Have you ever looked at a clock and wondered if what you are measuring is actually real? Not in a poetic sense, in a hard, scientific sense. You wake up, you follow a schedule built around this invisible thing we call time, and yet almost nobody stops to ask whether the way we experience time has anything to do with the way time actually works. Physics tells us something most people find deeply uncomfortable. Time is not a river flowing in one direction at a constant speed. It bends, it stretches, it is tied to mass, to velocity, to gravity. A clock on top of a mountain ticks measurably faster than a clock at sea level. A clock inside a GPS satellite has to be corrected every single day because it drifts from clocks on the ground. These are not theoretical curiosities. They are engineering realities we depend on right now as you watch this. And the roots of the mathematical framework that made this understanding possible trace back to a young Frenchman born in 1623 who was thinking about infinity, infinitesimals, and the nature of continuous motion long before Einstein or Newton had finished the picture. Blaise Pascal was not a mystic who occasionally dabbled in science. He was a precision instrument. At 16 years old, he had already produced a formal proof in projective geometry, a branch of mathematics concerning what happens to shapes and relationships when you change the point from which you observe them. Projective geometry is fundamentally about how the same underlying reality can look completely different depending on your reference frame. That idea, that measurement and observation are always relative to a position in space, is one of the conceptual ancestors of everything we now know about relativity. Pascal did not know he was laying groundwork for a physics that would not be formalized for another 250 years. He was just following the logic of mathematics wherever it led. When Pascal was 18, his father was a tax commissioner in Rouen, and the work required enormous amounts of manual arithmetic. Pascal watched his father spend exhausting hours on this labor and decided the problem could be mechanized. He spent 3 years building a machine that could perform addition and subtraction through interlocking gears and a carry mechanism. This was the Pascaline, completed in 1645, one of the first functional mechanical calculators in history. He built approximately 50 prototypes before arriving at a reliable version. Pascal was asserting that mathematical reasoning could be separated from the human mind and embedded into physical structure. He was externalizing cognition into matter. That idea would eventually become the foundation of computer science, information theory, and every digital system running modern life. In the early 1650s, Pascal became involved in a correspondence with Pierre de Fermat about a problem gamblers had brought to mathematicians. If a game of chance is interrupted before it is finished, how should the stakes be divided fairly? This seems trivial. It is not. To solve it, Pascal and Fermat had to develop a coherent mathematical framework for reasoning about events that have not yet happened. They had to assign numerical values to possible futures. They invented probability theory. And what probability theory is, at its core, is a mathematical description of time's arrow. It is a formal system for navigating the fact that we exist at a specific point in time and cannot directly observe what has not yet occurred. Before Pascal and Fermat, there was no systematic quantitative method for reasoning about future states of a system. After them, there was. Every risk model, every weather forecast, every actuarial table, every quantum mechanical calculation that gives us probabilities of particle behavior, all of it descends from that correspondence between two 17th-century mathematicians arguing over gambling debts. Now here is where it gets strange, and I want you to pay close attention. Pause for a moment. Before the age of 30, Pascal contributed to projective geometry, invented a mechanical calculator, and co-founded probability theory. 3 pillars of modern science, built by one person in one compressed lifetime. Have you ever felt like you cannot find the pattern in your own life? Like the dots refuse to connect? Pascal spent his entire career finding patterns in things that appeared to have none. If that resonates, write, "I want to see the patterns" in the comments right now. You are not alone in that feeling. Every comment you leave also helps another person watching realize they are not the only one asking these questions. What Pascal discovered about the mathematics of change also revealed something about infinity that disturbed and fascinated him equally. He worked on what we now call infinitesimal calculus, the mathematics of continuous change and of quantities that approach zero or infinity as limits. Newton and Leibniz are usually credited with formalizing calculus, but Pascal's work on summation of infinitesimal areas, particularly his analysis of the cycloid, the curve traced by a point on a rolling circle, was a direct and acknowledged influence on both of them. He solved significant portions of the cycloid problem in 1658. What calculus ultimately tells us about time is that continuous change cannot be reduced to a series of frozen instants. Time is not a sequence of discrete moments. It is a continuous flow, and the relationships between quantities changing within that flow are described by differential equations. Those equations are the language in which both Newton's mechanics and Einstein's relativity are written. Pascal was learning that language before the grammar had been formally codified. In 1647 and 1648, Pascal turned to a problem in physics that was also, in disguise, a problem about the relationship between observers and the physical world. Torricelli had demonstrated that a column of mercury in a sealed tube would drop to approximately 76 centimeters, leaving what appeared to be empty space above it. The orthodox view, derived from Aristotle, was that nature abhors a vacuum. Pascal was unconvinced. He reasoned that if atmospheric pressure was supporting the column, then at higher altitudes where the air above was lighter, the mercury should sit lower. He could not climb the mountain himself due to his fragile health, so he arranged for his brother-in-law Florent Perrier to carry a barometer up the Puy de Dôme on the 19th of September 1648. The result was unambiguous. The mercury column was shorter at the summit by over 3 centimeters. Pascal had proven that air has weight, that the atmosphere exerts pressure, and that this pressure varies measurably with altitude. He had measured something invisible by observing its effects on something visible. This is the core methodology of modern physics. You cannot see gravity directly. You can see what it does to a falling object. You cannot see time dilation directly. You can see what it does to a clock. If you have been finding value in this kind of deep scientific exploration, I want to invite you to subscribe to this channel. This content takes real research to build, and when you subscribe, you are telling the algorithm to keep bringing it to people who are genuinely curious about how the world works beneath the surface. There is a community here of people who want to understand the actual structure underneath the stories we tell about history and science. Hit subscribe and the bell notification. You belong here. The unit of pressure in physics is named the Pascal in his honor. 1 Pascal equals 1 Newton per square meter. His barometric work had a direct and underappreciated link to precision timekeeping. Huygens, who formalized the mathematics of the pendulum clock in 1673, was working in the same intellectual environment Pascal had helped shape. By establishing that the atmosphere is a variable physical medium with properties that change measurably with position, Pascal was contributing to the understanding that measurements are never absolute but are always made within a physical context that must itself be characterized. That understanding is the backbone of metrology, the science of measurement, which underlies all experimental physics, including the experiments that eventually prove time itself is not absolute. By 1654, Pascal had accomplished more in mathematics and physics than most scientists accomplish in a lifetime. Then he stopped, abruptly. A handwritten note describing an intense 2-hour experience on the night of the 23rd of November 1654, known as the Memorial, was found sewn into the lining of his coat after his death. He had carried it every day for 8 years. He would die in 1662 at 39. His later writing, the fragments collected posthumously as the Pensies, is concerned with the nature of human reason and its limits. Pascal did not abandon rationality. He interrogated it. His famous wager, routinely dismissed as naive theology, is actually a decision-theoretic argument, an application of expected value calculation to a question of belief under radical uncertainty. It is recognizably a product of the same mind that invented probability theory. He was not abandoning the mathematical framework. He was applying it to a domain that mathematics alone cannot resolve. The limits of a method are part of the method's complete description. Time is not what common sense tells you it is. It is not a fixed, universal, absolute backdrop against which events occur. It is a physical dimension warped by mass and velocity. Clocks at different gravitational potentials tick at measurably different rates. Events simultaneous in one reference frame are not simultaneous in another. These are measured facts, confirmed by experiments that Pascal's methods of careful quantitative reasoning made possible. The 300 years between Pascal's measurements on the Puy de Dôme and the atomic clocks that now confirm relativistic time dilation are a single continuous thread of people applying the same discipline. Measure carefully, let the mathematics speak, follow the logic wherever it leads, and do not flinch from what you find. Pascal did not flinch from the vacuum, did not flinch from probability, did not flinch from infinitesimals. That discipline is the most important thing he left behind. The question it leaves open for you is this: What assumptions about the nature of your own reality are you carrying around without examining them, the same way 17th century scholars carried Aristotle's claim that nature abhors a vacuum right up until a mercury column on a mountaintop proved otherwise?